2.2 Physiology by Leo Whedon. For this assignment, we had to explore the physiological responses of the body systems to exercise and training. What is steady state exercise? Adams et al. States that upon exercise, you increase your energy usage. This reflects in the increase of oxygen consumption. Under certain conditions where the work rate is constant, the pattern of this increased oxygen consumption shows an initial rise, then levels off. For example, if you undertake a 20-minute continuous same speed jogging or swimming. Steady state exercise. Prior to exercise, the heart beats between 60 to 80 beats per minute in untrained men and women due to the anticipatory rise. This is the increase in heart rate that typically occurs before activity. It results in an increase in the sympathetic nervous system, causing the adrenal gland to release adrenaline and noradrenaline. The heart rate increases during exercise, as it does so in relation to the intensity of exercise performed due to the receptors that detect changes in the body. The information is picked up from the receptors and then sent to the medulla oblongata via the RCC. This is then sent. The impulse is then sent down the nerves, the SA node. The SA node is then sent a message to increase heart rate to allow more oxygenated blood to be delivered to the working muscles during exercise. Stroke volume. Stroke volume is the amount of blood pumped to the left ventricle of the heart in one contraction. Stroke volume reaches a peak during submaximal exercise, and it does not increase further during maximal exercise. The greatest increase in stroke volume occurs in the transition from rest to moderate exercise. During minimal exercise, stroke volume does not increase as the left ventricle is already full. Cardiac output. This is the amount of blood pumped to the heart per minute. During steady state exercise, the cardiac output increases initially along with the heart rate and stroke volume, but eventually also plateaus because the heart rate remains at a constant speed to meet the demands of exercise. Blood pressure. Blood pressure is the pressure of circulating blood on the walls of the blood vessels. There are two different types of blood pressures: systolic, which is the pressure in the arteries, and diastolic, which is the phase of the heartbeat when the heart muscle contracts. During steady state exercise, dilation of the blood vessels in the active muscles increase the muscular area for blood flow. Blood flow is the amount of blood reaching parts of your body. Blood flow increases during exercise as the working muscles need a greater amount of blood in order to supply them with the energy. Thermoregulation. This is the body's internal body temperature. There is an increase in plasma volume due to steady state exercise, which supports the sweat glands function during heat stress and maintaining the correct plasma volume for demands of exercise. Venous return. During exercise, the blood pressure in the veins is not high enough to increase the level of venous return, and so maintains the high stroke volume and cardiac output which exercise requires. So muscular contractions air the venous return. And finally, Starling's law. Stroke volume increases in response to an increase of blood volume filling the heart. This stretches the ventricle walls, causing cardiac muscles to contract more forcefully. The stroke volume may also increase due to a greater contraction in the cardiac muscles during exercise. Vascular shunt during steady state exercise. This is the distribution of blood around the body. During exercise, the vascular system redistributes blood to the areas with the greatest demands of oxygen away from areas with the lower demands of oxygen. Vascular vasodilation and vasoconstriction during exercise. When we exercise, our heart and breathing rate rises rapidly, and the blood vessels in our body vasodilate and vasoconstrict. So when the body is working hard, the blood vessels will vasodilate, meaning there are greater amounts of blood flowing to the muscles to supply them with oxygen. However, when there is enough blood distributed to the blood vessels through the blood vessels, vasoconstriction takes place, meaning they close up, not fully, to reduce the blood flow and the backflow as well. Tidal volume. Tidal volume is the quantity of air that is inhaled and exhaled with every breath taken. When using Mo Farah's resting heart rate of 33 beats per minute, you won't need as much air inhaled every minute taken compared to the average adult with a resting heart rate of 70 beats per minute, who will have to intake more air to supply the oxygen to the working muscles. Aerobic system. In the ATP, the pyruvic acid and coenzyme A gives an AC CoA by detecting O2 and pyruvic acid. Glycolysis is the breakdown of carbohydrates into pyruvic acid and resulting in the production of ATP molecules. A total of 10 chemical reactions are required to convert carbohydrates into pyruvic acid, which takes place in the muscle's sarcoplasm. One yield is needed in a sarcoplasm when oxygen is present. The cells will perform more oxygen respiration, so aerobic respiration. To fuel the process, to fuel the process, there must be carbohydrates, fats, and proteins enabled to provide energy to the working muscles. The system has a duration of hours, so during steady state exercise, there will be a byproduct of CO2 and H2O from sweating and heavy breathing to be able to last the duration of 20 minutes, which is steady state exercise. Muscle spindles. There's an organ placed within the muscles which communicates with the central nervous system. Its purpose is to detect when the muscle is in a state of contraction. During muscle contraction, tension changes in the MS and is relayed to the central nervous system, which deals with the information by increasing contraction or relaxing the muscles. Golgi tendon organ. This is a proprioceptor located within the tendon and are sensitive to stretch. Golgi tendon organs send information to the central nervous system concerning the strength of a muscle contraction. During exercise, the tension provides sensory information, allowing smooth and coordinated movement patterns. Dissociation curve. The effectiveness of hemoglobin oxygen binding can be affected by several factors. Factors can be viewed as having an effect of shifting or reshaping the oxyhemoglobin curve of a typical healthy person. During steady state exercise, the standard curve is shifted to the right by an increase in temperature, or a decrease in pH, acidity, concentration, so that more oxygen can be unloaded to supply the air to the active muscles. Hypothesis. There are three different types of hypothesis: null, two-tailed, and single-tailed. Null hypothesis. This is the hypothesis that there is no significant difference between the specified populations, any observed difference being due to sampling or experimental errors. Two-tailed is the standard test of significance to determine if there is a relation between variables in either direction. And then finally, single-tailed. This is a statistical test in which the critical area of distribution is sided so that it is either greater than or less than a certain value. During our experiment, we firstly measured the client's pre-workout heart rate, blood pressure, O2 saturation, and lactate. After this, we got the client to warm up for 2 to 3 minutes to be able to avoid stiffness during steady state exercise. Then the client worked for 20 minutes in his submaximal state of 70 to 80% of his maximum heart rate, which is around 159 to 175 beats per minute. During steady state exercise, we again measured the client's heart rate, blood pressure, O2 saturation, and breathing rate roughly every 2 minutes, but also measured the lactate every 6 minutes, as we couldn't prick the client's finger every 2 seconds. Finally, measurements were taken for both 1 and 2 minutes after the client had completed a 20-minute exercise of steady state exercise. Moving on to types of graphs we got. For heart rate, at the minimal stage of exercise, 2 minutes, we can see that the heart rate is around 75 to 130 beats per minute, meaning the data is quite tight and they are in a similar range to each other. However, as time increases, 8 minutes, the heart rate increases by an average of 25 to 80 beats per minute, as they are at present time working at 70 to 80% of their maximum heart rate. Towards the end of steady state exercise, we can see that the data has plateaued due to the heart rate staying at a steady state in order to continuously exercise at 70 to 80% of their maximum heart rate. When looking at the data, we can see that Josh M at pre 1 minute is at around 105 beats per minute, which is 15 beats per minute higher than the average. So stating this, we can disregard the piece of data. Maybe the reason behind this data may be down to the fact the participant warmed up before taking part in the experiment, which could have potentially increased his heart rate too high. When observing normative data, we will see an increase at 2 to 4 minutes, but then plateaus around 6 to 20 minutes, as they will be working at 70 to 80% of their maximum heart rate, which is steady state exercise. But at the end of the exercise, we can see a decrease due to the heart rate returning back to normal. In the first 10 minutes, the test subject / client's heart rate shot up from 88 beats per minute in the first 2 minutes to 187 beats per minute after 10 minutes of exercise. 10 minutes in, the subject is not working in steady state exercise. He is working at his 90% maximum heart rate, so we told him to decrease in intensity, therefore bringing his heart rate back down to steady state level, which is working at 70 to 80% of his maximum heart rate.